let me begin by hopefully short summary of something that I said in the first lecture. So let's call this summary. So first of all, we have a notion of Ruelle resonances for an Anosov diffil phi, and the idea was to have an asymptotic expansion. So if we look at correlations, phi composed with phi n, g, there should be an asymptotic expansion. Let me copy it like this. Here there is some multiplicity. I call it L rho in my notes. So there's some C rho I Fg and some Ni and some rho n. And this is for, say, for Fg smooth. And basically, well, I should point out that one of you, in fact, Faure made me realize that it's not at all trivial that such an expansion even exists in general. So what we seen yesterday, well, on the other hand, I consider the cohomological equation. Well, actually, I consider the case of the torus. So let me just say that for the torus, for linear, well, for automorphisms, for hyperbolic automorphisms, the torus of the 2, so phi. Basically, we prove the proposition that the only Ruelle resonance is 1, the value 1, which is the leading, always there is the leading term. I haven't written here, but R contains always, in a situation where we have a volume preserving system, always contains 1. The only Ruelle resonance is 1, which means, essentially means that if f and g are smooth, in this case, then for every r positive, there exists some constant that depends on f and g, such that the correlation the size of the correlation is less than this constant and then some power. So R can be arbitrarily large, and here's for f and g, which well, I'm sorry, here of course there is the 1, and to get rid of the 1 I will always take f, say, 0 average. Simplifies the formula to take f of 0 average. So this is more or less what we had, right? And this was followed from another proposition that basically, well, basically says the following. So if x alpha, where alpha is a vector, alpha 1 ddx1 plus alpha 2 ddx2, if alpha is a Diophantine vector, then the cohomological equation x alpha u equal f has a infinity solution u whenever f is infinity and 0 average. And in fact, the statement was more precise. It was like there is a with loss of derivative 1. And then in particular, there was the fact that the the unstable direction of a linear Anosov. So if we look at the case of the torus, and we have an hyperbolic automorphism, the expanding direction is in fact Diophantine with a with the smallest possible Diophantine exponent. So we have a loss of derivatives actually 1. But that was more or less the situation. So one thing I want to point out here is that, of course, one can ask, what about nonlinear automorphism, Anosov automorphism of the torus? And I should point out that for nonlinear Anosov automorphism of the torus, well, there is a paper, a relatively recent paper by Giulietti Liverani, that motivated, well, started, in some sense, started a lot of work around this problem of Ruelle resonances and related consequences, well, and especially applications to cohomological equations and ergodic theory of the unstable direction. So the point here is that in the linear case, we can do Fourier analysis on this side and get result on this side. But in the general nonlinear case, the Fourier analysis for the unstable is not available. So this method studies directly. So they study directly the action of the Anosov differ, and this is also the approach. Of the paper of the work I quoted by Faure, Gouezel. Okay, so this is just well, the approach for Gouezel and Lanneau, which is more relevant to what I'm discussing, which is exactly this business of Ruelle resonances for pseudo-Anosov maps, still linear case.
What is a nonlinear?
Well, nonlinear means any smooth Anosov map differ of the two torus. So, for instance, you can take.
The definition of Anosov?
Oh, the definition of Anosov is that it's supposed to have an expanding. It's supposed to have a distribution, a continuous distribution which is expanding, and a continuous distribution which is contracting. So, in some sense, you can say it's like an hyperbolic automorphism. The hyperbolic automorphism has a linear constant expanding direction and a linear constant contracting direction. Now, this can be replaced by continuous distribution, continuous field, which are expanded or contracted, uniform. So is a uniform hyperbolicity. So, for instance, you can take a linear automorphism, an hyperbolic automorphism of the torus, and you can perturb it a little bit. So, just a small perturbation will still be Anosov, and it will be a nonlinear Anosov, and that's of course. No. Okay, so pseudo-Anosov is the analogous of the Anosov of the linear Anosov of the automorphism situation in higher genus. One can consider also nonlinear pseudo-Anosovs, meaning that small perturbation of pseudo-Anosov. But we're not going to go into that territory. So here we are. This is just a remark that the theory that studies directly the Anosov action, instead of going through the cohomological equation, is more general and more powerful, and this is in some sense the point of these methods. But in the linear case, we can understand what's going on in more detail just by looking at the cohomological equation. So, all right. So let me. Any other questions? Okay. Let me go into what changes in higher genus. So, so the main point is the following: is that the cohomological equation here we can solve. Here we have this statement that says we can solve for any f0 average. We can solve without any obstruction except for the. I'm sorry, no obstruction except for the average. So if the average is 0, you can solve. And recall that as I explained in last lecture, what we want to do is to iterate the solution, right? We want to solve and then solve for the solution and so on, and in fact construct what I call iterated solutions and classify the iterated coboundaries. So in other terms, let me recall that iterated coboundaries are f's such that they are equal to kth derivative. So these are k iterated coboundaries. That's what we call it, some sort of important notion. So in higher genus, what will happen is that there will be many obstructions to solving this equation, and of course, when we try to solve more and more, this number of abstractions will tend to grow even farther. So the main point here is that we have obstructions to solutions. So many, in fact, infinitely many abstractions to solutions. So this is the part that I'm going to try to explain now. So before I state the theorem, I have to go back to the issue of regularity. In order to state the theorem, I have to tell you what is smooth on a higher genus surface, or at least what is a decent class of smooth functions that is allowed. One can discuss whether it's the largest class, probably is not, but anyway. So the main point is, so smooth spaces of, so here is about spaces of smooth functions in a genus higher than 2, where we have singularities. Now, the most fundamental idea that comes up in what I did is the following fact. Imagine that P is a singularity, and near P we have a canonical coordinate Z, complex coordinate, and the holomorphic differential that is associated to the translation structure will look like zk dz. So here, this means that the angle is 2 pi k plus 1. Now this means that we have a branch cover. So we have a branch cover z goes into zk plus 1 over k plus 1 is a local branch cover, and we have to define the space S that depends on the holomorphic differential H, or if you want, depends on the vector field x and y, which is given by infinity functions that are locally lifts of infinity functions under the cover. So this can be just. Okay, so yes, so these are functions on the higher genus surface. On the higher genus surface, there is a local coordinate. Well, there are several local coordinates at singular points. They have to be infinity on the higher genus surface, but also they have to be at the singularities. They have to be lifts of infinity functions under this branch cover. Another way of saying this, I will detail this more. Another way of saying this is that. Basically, if we look at the Taylor the Taylor expansion at p singular point, well, it's a function. It has to be a function. Has to be a function of zk plus 1 and z bar k plus 1. So that's basically what happens. For instance, example. If we have a simple zero, so the simple zero is z dz, so simple zero, then locally the function z does not belong to this space, but z squared does, because the function z, so the cover here is z squared, and the function z is not a lift, it will be a lift of a square root, which is not infinity downstairs. So this is just a class of spaces. So, and inside these spaces, well, I mean, related to these spaces are the Sobolev spaces. So, Sobolev spaces, Ws xy of m, then basically these are the spaces of f's such that x, well, it's a bit, so for s integer it's just a xi, yj, f is in L2 for I plus j less than s. So this is for s natural number. There is a way that one can discuss extension to s non-integer, real number, and but I'm not going to bother with that. So essentially, the condition is that certain number of derivatives with respect to the vector field x and y are in L2, and then there are the dual spaces. W minus s. These are just the dual spaces of these spaces, and these are spaces of distributions. And in particular, any space Ws, W minus S, xy, is going to be inside the dual space of this. So any element which acts on functions with s derivative also acts on this on all these functions here that I call s. So I usually call this tempered distributions, but just to find a word. So these distributions have to have some nice behavior of the cone points. They cannot do whatever. But these are all the spaces that I need. And you see that the main point is that essentially these spaces have to be defined in some way. They are like smooth, but with respect to the chart given by the branch cover. So that's essentially the idea. So they are smooth, but as a chart, you don't use the smooth chart on the surface. You use the chart given by the canonical coordinate and related branch cover. Okay, so with this notation, we have the following theorem. Well, maybe I should, before the theorem, I should give a definition. The definition of what is an invariant distribution. So an element D which belongs to the dual of this S, and of course it could belong it could belong to W minus S, is called X invariant if xd is equal to 0. Now, if you're not familiar with working with distributions, so what is it?
Sorry,
Yes?
which manifold is that? Is it the cover or?
No, M is always my surface. M is always my homogeneous surface. The cover is entirely, I'm sorry, I wasn't quite explicit there. So the cover is entirely local. So you take a little disk around the cone point, and the canonical coordinate for the holomorphic differential will give you a local branch cover over a disk in the small disk in the complex plane, totally local. There is no global cover. It's just a local. It's just to say that what I said here, that essentially the Taylor expansion at the cone point is restricted in a certain way. That's enough to make the analysis work. Probably one can do better in the sense to allow larger spaces of functions, but yeah.
So what are you taking L2?
Yes, the L2 is the L2 of the M with respect to the area. Yeah, thanks. Yes?
Can you explain the inclusion why the dual of why W minus S X Y?
Well, that's like, yeah, that's you have to compute. That's a fact. I mean,
Well, maybe you should just remind isn't the distribution usually defined as a function of C infinity functions? I mean, you didn't assume that the W is a C infinity function. So.
Yeah, no, but distribution are linear functions which act on C infinity functions. That's right, but they can act also on larger spaces. Like for instance, the delta distribution, it's a measure, so it acts on continuous functions. Of course, it's also a distribution, so it acts on infinity functions. So some distributions are more regular in the sense that they act on functions which are worse than infinity. So there is a whole hierarchy, a scale of regularity, and this is measured by these dual spaces. So all the objects we are going to see, all distributional objects we are going to see, act on this space S, which is a small space of functions which are not only see infinity everywhere, but moreover they have a constraint on the Taylor expansion. But in fact, they all act on this space, but in fact many of them will act on, finitely many of them will act on spaces W minus S, which are larger spaces. The functions are not infinity, or they are not even, they are just up to derivatives and so on.
So the F in the definition of WS, the F also needs to be in your space SXY or not?
Well, the F is in L2, and all the derivatives are in L2.
Does it satisfy this additional condition on the singularity?
Well, if you compute what this means, it will verify this additional condition on the singularity only up to a finite order. So the first part of the jet will be like this. But then there will be no jet because the function is not infinity. So there will be a jet, like a Taylor expansion, a Taylor polynomial, up to some order which is not exactly S, it's slightly lower because of the usual business, but Sobolev embedding and etc. And up to some order will be exactly like this, but then whatever. So in some sense it's a weaker restriction on the function than, of course, being in S. S is the smaller space. So you can, if this is too technical, you can think that S plays the role of C infinity, and WS plays the role of the usual Sobolev space, which you can think in terms of Fourier expansion on the torus, like asking that the Fourier coefficient decay at certain polynomial speed. And W minus S are just the dual spaces. So these are just a linear function acting on the WS's. Yes?
What is the dual space? I mean, I just vaguely remember that there is some topology where it's the same.
Yes, that's right. That's a good point. What is a topology? In this space comes with a natural way of putting, an inner product. So WS is an Hilbert space.
Actually, I meant the S prime XY. What is S prime XY?
Oh, S prime XY. Well, this premise-wise, yeah, there is a topology like a Fréchet kind of topology. So it's like infinity. You have a family of norms. The norms are these ones. So the statement here is the following: if I take the intersection over S positive of WS, this is S. So on S, you have all the norms that come from WS. WS has a norm which essentially is like you take the L2 norms of these derivatives and add them up. So more precisely, you want to, there is an inner product which is FG WS XY. This is equal to the sum less than S of the L2 norm of xi, yj, or maybe you cannot read here, f xi, yj, g, L2. So that's the usual. So you just take this derivative and then multiply them, integrate them, and you get an inner, and sum, and you get an inner product. So that's the inner product. So these are Hilbert spaces, but this is just Fréchet. So it has a countable, it's like infinity. It has a countable sequence of norms that define the topology. Like infinity. It's the same exactly, so if you don't like this, it's like you think it's infinity with some Taylor condition, the Taylor coefficients at the singularity that you cannot really get rid of. Other questions? Yes? Okay, so what is an invariant distribution? Well, an invariant distribution is a linear function on these spaces, either this or that. Of course, again, there is an inclusion, as I remark here. So if the second condition is true, the first is also true, which is X invariant in the sense that the Lie derivative in the flow direction is 0. So this means the following. It means, translated into, this is 0 as a function. So it means that for every f that belongs to S, D is 0 when evaluated on XF. That's by definition. By definition, okay? So that's it. That's the notion. And now the theorem says that the following, so let me write it properly. So there exists a finite dimensional space I minus S X. This is in W minus X of X invariant distribution such that, well, there is also a loss of derivative, yeah, such that for every f in WS xy, and this is going to be good for S larger than some S0. I will comment on that in a moment. There exists U solution of XU equal F with U that belongs in WT XY with T less than S minus S naught. So this S naught is loss of derivative. Loss of derivatives, that is. And while with some, also with some estimates. So the T norm of U is going to be less than some constant that depends on S and T, the S norm of F. Oh, I forgot the most important thing, of course. For every F which such that F belongs to the kernel of I minus S X. So what does it mean f belongs to the kernel? It's a short way to say that all elements of this space of invariant distributions vanish on f. So you should consider in the case of the torus, we had exactly one element that was the mean, the average, that has to vanish to be able to solve. In this case, we have a finite dimensional space. Now, the point is that this finite dimensional space has no dimension 1. So this theorem still doesn't say that, but I'm going to yeah.
Wait, why does U have less derivatives than F?
U has less derivative than F. Well, this is a short way of I don't know if what is the best way to answer, but you may remember in the case of the torus, there were small divisors coming from the Diophantine. The Diophantine condition was there to control some small divisors in the Fourier expansion. So you can say that this is due to small divisors. Small divisors are an expression of the fact that the dynamics has some rate of return, and this causes some loss of regularity. So,
I mean, it's surprising given the direction of the equation, I guess. I mean,
well,
differentiating something and getting something that's like more differential.
yes, you're totally right. But imagine there are even objects that are very rough, and whose derivative is 0. So that's a kind of extreme situation, right? So you can think in this sense that when you take the derivative along x, there is some junk in U that sort of gets annihilated, and the result is smooth. Yes.
Can you formulate this just in terms of Sxy?
What?
I mean, can you inject intersection over all S over there? So my question is, this Ix minus S, is it in that case C infinity functions also?
Well, all this is a finite differentiability. If I take f in the space S, in the space calligraphic S, the space of say infinitely smooth functions, then I don't automatically get a solution which is infinitely smooth. The reason being that I have to satisfy these conditions. Now, as I ask the regularity to go up, the dimension of this space goes to infinity. So I could say the theorem that is like this. So this is probably what you want to know. So corollary, there exists an infinite dimensional. I mean, it's not quite, technically speaking, it's not a corollary because I haven't proved that this space, what is the dimension of this space yet. I'm going to discuss that in a moment. But corollary, essentially corollary, there exists an infinite dimensional space Ix of all X invariant distribution in S prime, such that if f belongs to S and in fact it belongs to the kernel, and f belongs to the kernel of this Ix, then the solution U is also in S. So the price one pays is this. There is no way of avoiding these obstructions to go up. Their dimension will go up to infinity. But it's not enough that the function is infinitely smooth. You also need to satisfy all these constraints.
Do you have conditions on M? It's assumed to be pseudo-Anosov in some ways?
Right, no, yeah, this is a theorem sort of stated without assumptions on X, and my aim was to detail in subsequent remark, and I'm going to do it now, who proved what and what in what cases. So, yeah, so this is, at this point, I haven't told you what are the conditions on X. So in some sense, this theorem misses some important information. So so conditions and remark and sort of conditions on X, and if you want historical remarks. So this goes more or less like this. So in my 97 paper, I proved this for almost all directions, on every translation surface. But this didn't include the pseudo-Anosov case. So this is just almost all directions. Then this was done by Marmi, Moussa, Yoccoz. This is paper in 2005, and this was for under a certain small divisor. Well, not really, but under certain small divisor condition called Roth type, and this includes the pseudo-Anosov case. Of course, I say pseudo-Anosov case, I mean the stable and unstable directions of pseudo-Anosov. Now here also a comment, and here as not, here was probably 9, and then it was, I could improve it to 3 plus something. Here as not was maybe 1 plus bounded variation. And then there have been efforts to improve this loss of derivatives. And the idea is that the loss of derivative, so analysts care about these things. What is the loss of derivatives? And the idea is that the loss, ideally, S naught is 1 plus epsilon for any epsilon, at least for Anosov, for pseudo-Anosov case, pseudo-Anosov. And also for the generic case. And so there is some progress in that direction is in my 2007 paper, and then there is a paper by Marmi Moussa in 16. And I have to say that these papers don't quite get to that in full generality. There is an improvement also by Faure, Gouezel and Lanneau. I would say they prove it in the pseudo-Anosov case. So for people that are interested in loss of derivatives, this paper contains, this work also contains this, finally contains this optimal loss of derivatives in the pseudo-Anosov case that has eluded at least some of us for a long time. Okay, so any other questions about the logical equation?
Why is one perception representation?
Excuse me?
Why is the best one?
Well, yes. Why? Well, let's put it this way. So that's it's not hard to see. It's sort of, let's put it this way. It's an exercise in the case of the torus that, given the nature of real numbers and approximation of irrational numbers by rationals, that the best one can do in the torus is 1, and 1 plus epsilon in the generic for almost all. So you compute, you see it's already in the torus, in the Sobolev, for instance, the Sobolev spaces, you cannot do better than 1, and so you don't expect to be able to do better than 1 in other cases. And yeah.
Is there a way, so you could also introduce a bigrading on the Sobolev spaces to account for the x and y direction?
Yeah.
And then you could allow roughness in the one direction. You could, in principle, have sharper statements. to that?
Yes. That's exactly what this Faure, Gouezel, Lanneau do. They do have result where the regularity is, they distinguish regularity between the two directions, and there are many things that I could also add, right, to the statement, but yeah, I don't know. I'm not sure, unless you have to tell me what is the application, in some sense. Yeah, no, sure, this can be refined by looking at regularity in a distinct way depending on the direction. Okay, so now the issue is that the space I x and I minus s x is not trivial. So now I have to discuss why is that. I mean, how do we deal with this? Well, the point is that, first of all, the point is, well, there is a simple remark that it doesn't help yet, which is the fact that if D is X invariant, then YJD is X invariant for all J. Just because X and Y essentially they commute. Now, of course, this is a tricky thing to say, they commute, because you can also say they don't commute, right? If you look at the flows, they certainly don't commute. So they commute enough to make this statement true. Let's put it this way. So they commute, for instance, they commute on functions which are sufficiently irregular. So if, in the sense that if f and g belong to the space W2, then certainly it's true that yxf is equal to xyf. So but you need the functions to be sufficiently irregular in this specific sense. Okay, so this is a remark that, of course, doesn't help with this non-triviality, because if we take the invariant measure, we take derivative, we don't find anything new. It just suggests a mechanism to generate more distributions. If we have one of them,
first of all, there's no G there.
excuse me?
You had a remark that if F and G are in W2, then they commute.
Well, then y and x they commute on.
G is
F and G are two functions in the space W2. Oh, I'm sorry. There is no G. Yes.
Can you explain why this is true?
Calculation. I mean, the main point is that.
What's special about 2? It's just the fact that
Well, what is special about 2? Well, first of all, if I put only one, I mean, I could put here S, right? My space of infinity functions. If I put only one, these two things are not even defined. They are not even L2 functions. So another statement is that if the reason I put F and G is that if F and G are in W1, then it's true that X, F, YG is the same as Y, F, X, G. So that's another, and in fact, more important manifestation of the commutation. But this commutation, you see, we need some Taylor expansion at the cone points. Now, one thing that someone may say is that, well, how do you prove this theorem? You do the same as in the case of the torus. You look at the eigenfunctions of the Laplacian, and then you exactly do the same. Well, that doesn't work because the commutation is not sufficient to have such a nice situation that the eigenfunctions of the Laplacian are also eigenfunctions of the vector field. So eigenfunctions of the Laplacian are not going to be eigenfunctions of the vector field, generally speaking. And in fact, it is known that the vector fields have no eigenfunctions whatsoever in general. generic situation. So just as a side comment, the plan that worked for the torus is not going to produce anything in hygienius, just because of this. Or the commutation is there, but it's not sufficient to carry out the same mechanism. So the same kind of proof with Fourier expansion and everything. So okay, so I really try to explain now how we get the non-triviality, and eventually boils down to a remark that Simeon Philip made this earlier, that the point is in hygienius that we have many holomorphic differentials. So this is one way of viewing this, but in order to get there, by the way, what time I'm considered to have started? I haven't checked.
I mean, you can go the other round.
Okay. Okay, so the main point is that we can associate to every X invariant distribution a cohomology class So this is the essential step. And then once we have that, so we have this we have this map from distributions. So here is in IX, and here is the cohomology class. This will be in H1 a priori MC. And in fact, this map will be basically surjective, not quite. I mean, remember that I'm restricting these distributions to belong to some certain space. So in particular, there are these restrictions on test functions of the singularity and everything. So they are supposed to be tempered, etc. So this map is, so the main claim, I haven't defined the map, I will go in a second, is that this map from IX to H1 has a range equal to the set of classes in H1 such that, well, the wedge, they have a wedge with the contraction of area with respect to X equal to 0. Well, I'm not sure this is entirely correct. Yeah, I think it should be. But basically, there is a condition like this. For instance, if I look at the contraction with respect to y of area, this does not belong to the range. And basically, this is the only direction that does not belong. So that's the situation. So basically, the map to cohomology is essentially subjective. It just misses one direction. Yes?
Can you explain again how an X invariant distribution is a cohomology class?
Well, I haven't explained that. Yes.
Can you use that measure of the contraction?
Excuse me?
Can you explain this formula? I mean, what is the contraction of the?
Oh, this formula. Well, this is the usual product in. You can take this is a closed form, right? So I really mean this. So if you want, this is a class in H1 M R, and you just do the usual intersection in H1. So this is a cohomology class. Well, if you want, let me put here R, which is probably simple. So if you take the real part of this, then it will, I mean, it's more likely that my statement will be absolutely correct on the real part. So if you look at the map to the real part, this is a cohomology class, and this is a cohomology class. The contraction of the area So what is the contraction of the area with respect to the flow? It's just a one form. It's the one form that defines the foliation, right? If you want, it's either the real part or the imaginary part of your holomorphic differential. It's a closed form. It has a cohomology class, and there is a pairing. This is just the usual pairing of cohomology classes, the symplectic form, and this condition that the cohomology classes that can be represented cannot be, basically it's like saying that if we look at the form corresponding to the other direction, then that's not going to be in the range. So what I have to explain, what I want to explain here is how do we associate a cohomology class, and what is the basic reason that this is true. So it will be not too hard to explain why this is true. So first, how to define a map from invariant distributions to H1. Let me just do the real part. Of course, if I have it on the real part, I can extend it to the complexification. So the idea here is that we should work with one current. So I need to say something about currents. Now, distributions are linear functions on functions. Currents in general are linear functions, continuous, but forget about that, on forms. So a current is a linear. It's a linear function, functional on smooth forms. And again, here the notion of smooth has to be taken in this adapted sense. Well, of course, there are forms of different degrees, and we can talk about currents of different degrees and also of different dimensions, because the basic current is the current given by a submanifold or a piece of submanifold by integration. So, for instance, is a current of dimension 0 and degree 2. A curve is a current of dimension 1 and degree 1, and well, an open set, you can see the rest. And why is that? Well, clearly the dimension is 0. Well, there is a notion of dimension. The degree is related to the fact that a point acts on functions and two forms act on functions. So it behaves like a two form. And a curve acts on one forms, so should have dimension 1 and also degree 1. The degree, in fact, the usual rule is that degree plus dimension should be equal to dimension of m, should be equal to 2. Okay, so, but for all purposes of this discussion, you should think that currents are just forms with distributional coefficients. And with distributions, you can do whatever you want. You take derivatives. It's like free. It's a free for all, except that you cannot multiply them. But it's sort of operations. If you keep track of regularity and everything, all operations are allowed. So we are going to associate to D what is called the flux current, and this is just D multiplied times the contraction of the area. I will keep calling it the contraction of the area. This is really, again, as I said, is the one form that defines the foliation of X, which is the real part or imaginary part of the holomorphic differential. And this current is closed. So why it's closed? Well, because formally, if we do the exterior derivative of a contraction, what we get is exactly the derivative of the coefficient times the area. So basically, what you should do is that ignore the fact that D is a funny object, just put a function and check whether this formula makes sense to you. So if I take a function f and I multiply times the contraction of the area respect to x, then I should get that the exterior derivative should be a 2 form, and it's going to be the Lie derivative of D in direction of x times the area. This formula works as well for currents and says that if D is invariant, if D is x invariant, then this current, this one form with distributional coefficients, then it is closed. So the Durand theorem tells you that any closed current has a cohomology class. Now it's an amusing feature of this. Usually in the United States, when I say this, people say, no, it's an homology class. So there seems to be a cultural split. But the original Durand definition is that there should be a cohomology class associated to a closed form. Yeah?
When you put the D in front of the things, the parentheses, that's just
this D is the exterior derivative.
sorry, big D.
Big D is
That's just multiplication.
this dot is multiplication. Yeah, let me. Yeah, this is a good question. Let me explain how multiplication works. So multiplication was like this. So the D times Ix omega, Ix area, sorry, is supposed to be a one current, so it's supposed to act on one forms. But in this case, we have the area, and the area is sort of a reference form that never changes. So we have to act on alpha, alpha being a one form, right? So what we do is we take the wedge of these two one forms, we divide by the area. No, we don't divide by the area. Sorry. This is. Yeah, we want to start with the distribution. Yeah, we divide by the area formally, which means we find a function, and then D acts on this function. So this is the definition of the formula that I use here. D. What is D times this contraction? D being a linear function on functions. I want to find a linear function on one form. In order to do that, I have to use the fact that I have an area form which is fixed once and for all. And when I do this wedge, I get a 2 form. The 2 form is the area times the coefficient, and I evaluate the distribution of the coefficient. Maybe there is a simpler way of doing this, but yeah. Yes.
So you wrote that the map was arriving in H1 at the top.
Where?
Yeah, the map.
Here. Yes.
It's evaluating on one form. So it's a homological.
So here I take D, right, an invariant distribution, so D such that xd is equal to 0.
But you're defining it as the dual of a dual space of one form. You're evaluating this thing on one form. So why isn't it H1 at all?
D is a function of functions.
Yeah, I mean the result of this. D times Ix.
D times Ix area, it's basically a one form. So you could say it's a one form with distribution coefficient.
So why do you evaluate it on one form and not on one?
Because I use the definition that a current is a linear function on one forms. So I want to see how it acts on one forms. So there are these 2 points of views. On one hand, you can say a one current, a current of degree 1 is, in this setting, is just a one form with distributional coefficients, which is exactly what you see here. The other point of view, which is sort of equivalent and complementary, is that is a linear function on one forms. Well, this is special to dimension 2, but so I'm using the definition that this is supposed to be a function on one forms, that's the original DRAM definition, but probably is not intuitive, and maybe the US favorite approach that these are forms with distributional coefficients is more appealing. But the two are kind of equivalent if you take into account the dimension. So for me, one current is a linear function of forms, smooth one forms. Okay, so that's the way. So now I define the flux current. By the way, the flux current, you can do this with a measure, right? If D is an invariant measure, then it will have also a flux current, and the flux current will have a flux class. And the flux class is basically the class that measures the amount of liquid or flow that flows through cycles on the surface. So here we are on the surface, so you can measure the amount of flux in unit time that flows through cycles, and you get a linear function on homology, which you can interpret as a cohomology class. And so it's a very classical notion that goes back to Katok rotation class or Schwarzman asymptotic cycle. This is just extended to distributions in a rather straightforward way, and probably appears in many contexts. So, well, I guess I will go maybe a couple of minutes over time. So this will give, once this is a closed current, then it has a cohomology. It has a cohomology class. And that's defined to be D. What is the main reason of the possible point of views on the fact that this space of invariant distribution is not trivial? So this is a very important situation which distinguishes the case of homogeneous surface from the case of the torus. It goes more or less as follows. So assume for a moment that, assume for the sake of a sort of contradiction, that the equation xu equal to f as a solution, every f smooth and of zero average. So I'm not trying to give you a rigorous proof, it's just a sketch of what is the basic reason. So let's suppose that it works like in the torus. So this, of course, is not going to be true, but suppose that it does. Now, the point is that we have holomorphic, there are G, well, there's a G-dimensional space of holomorphic differentials form a G-dimensional space, right? And we can look at their coefficients with respect to the holomorphic differential giving the flat structure, giving the translation surface, are meromorphic functions. So there is a space which looks like generated by, say, 1, M1, Mg, right? Span of this. I take any holomorphic differential, I divide it by the holomorphic differential that gives me the translation structure, and I get a G-dimensional space of functions which are meromorphic. Thank you. And then the point is that basically what I can do, I can solve for these neuromorphic differentials. Now I can solve x ui equal to mi, provided the average of mi is equal to 0. These mi are going to be integrable. In fact, they are going to be L2, and I can do that. Now here I'm cheating a little bit, because the mi are not in my space, but they are not in my space only at the singularities, and I can solve locally at the singularities to get rid of that. So this I can do, and then I can just apply Cauchy-Riemann. To the above equation. And I get, well, x plus iy, x ui equal to 0. Well, again, a little bit of care to check that this is really 0 in distributional sense. But then I have enough commutation that say that x of x plus iy, I'm sorry, this I is a bad choice, k. And here is a d. So dk is an invariant distribution, is a next invariant distribution. One can not have to check that this is trivial, cannot be 0. This is, of course, you can say, well, these are linearly dependent. No, it's not hard to check that these are linearly independent, and they provide you with sufficiently many to make this statement true. That, of course, you have a condition, which is the average should be 0, and but this basically accounts for the missing dimension. So that's the okay. So plan for next lecture is to continue this. So this is the cohomological equation and cohomology classes of invariant distributions. So in the next lecture, I'll finish this discussion talking about k-iterated coboundaries in this setting, how to construct them, and then how to apply them to the Ruelle resonance question. And then in the remaining time, I'm not sure, probably I will discuss the generic case, so how Teichmueller flow can enter the picture. So far we are dealing with pseudo-Anosov, but one can say something about how Teichmueller flow also can enter the picture. I'm sorry for going over time.